Я думаю, сейчас уже будет проще, если я просто включу камеру, Сергей Константинович будет куда скетч писать, я запишу его и выложу.
Звук пошел. А что сейчас будет? Да, понятно. Захват экрана, да, я понимаю, но почему-то он не активируется. Да, захват экрана, он почему-то не активирован, хотя он единственный. Ого. Все активно. Химические, да, мы же не можем не разрешать здесь. А давайте мы будем вас на телефон.
На телефон, да. Ну, я не скажу просто.
Сейчас.
Сейчас мы злые. А у Кирилла сегодня экзамен, поэтому он не пришел. Надо было нам отменить, конечно, сессию.
Можно отменить.
Мы этих скольких не предупреждаем.
Сейчас переключу, подожди. Не хочет. Видно, Люда? Вот текст. Нет. Вот экран. Что в трансляции идет? А, то есть с камеры. Идет с камеры, да?
Да, с камеры. Ну, направьте тогда доску на, ну, вот камеру на доску, тогда там записывается. Ну.
Все, поняла.
Так, развернуть.
Камеру на доску. Сейчас я посмотрю, здесь шнурок дотянется. А, так Черепанов он ее тут притянул.
Можно попробовать развернуть.
В смысле вы будете писать на
Ну,
обычной
давай,
доске?
Да. Надо не пересесть туда.
О.
Видно, да?
Вот эти две центральные.
Здрасте.
Okay. Sorry for the delay. It's a problem due to reconstruction of our standard room. And now let me start once again. Let probably adjust a bit. I will speak about mechanism room. Rule of Wigton's conjecture. And last time I have defined moduli spaces of complex curves. And here, this is the moduli space of smooth genus G complex curves. With n-marked points. And we have discussed the simplest examples of such moduli spaces where these moduli spaces exist when 3G minus 3, when 2G minus 2 plus what is the best? 2 minus 2G minus n is smaller than 0, is negative. This is the Euler characteristic of a curve, genus G curve with n functions. And we require that this Euler characteristic is negative. And in this case, these moduli spaces exist and have dimension 3G minus 3 plus n, and they are complex orbifolds. So locally they are quotients of the complex vector space of this dimension modulo a finite group action. These are orbifolds. And we have considered several simple examples, like M03 is a point, just a point. Any triple of points on a projective line are equivalent to one another modular fractional linear transformations. M04 is the projective line with 3 points punctured. We may choose the coordinates such that these 3 points are the points 0, 1, and infinity. And one more example of a one-dimensional moduli space we have considered is the moduli space of elliptic curves, of genus 1 curves, with a single marked point, and this moduli space is an infinite tube. It's an infinite tube with two singular points, with two not singular points but two orbifold points. Each is a result of taking the quotient of complex line C modulo the action of a finite group, so that the whole space is just the complex line. The whole moduli space is just the complex line C considered modulo the action of the group SL2Z. Which is more or less now these spaces GN are first, they are very important. They are very important, like the complex projective space of arbitrary dimension CPN. And in contrast to projective spaces, they are very complicated. They have very complicated geometry. Topological structure. Which is in contrast to CPN. And our goal is to say something reasonable about the topological structure of these spaces, about the topology, about the internal structure. But looking already on the simplest examples, we see a very obvious property that none of them are compact, and it is usually very difficult to say something about the geometry and topology of non-compact spaces. The space M03 consists of a single point, and it, of course, it is compact. But already M04, which is the projective line, that is a sphere, two-dimensional sphere without 3 points, is non-compact. And M11 also is non-compact. So what we need in order to study the geometry and the topology of the spaces, we need to consider some compactification of these spaces, and the standard such compactification is the Deligne-Mumford one. Compactification. The Deligne-Mumford compactification of the moduli spaces. Of course, there exist a lot of different compactifications, but I would say that the Deligne-Mumford compactification is the canonical one. Consider, for example, in order to say what is, I will not define it precisely, probably. But let me explain what this compactification means. The first example is the one for the moduli space M04, which is just the two-dimensional sphere. It is a two-dimensional sphere without 3 points. The points are 0, 1, and infinity. If you have chosen the coordinate properly. And it is obvious what we should consider as its compactification. 0, 4. Infinity, and the compactification M04 bar is just the projective line. We simply add these 3 points to the which are punctured from the original moduli space. We add them and obtain the two-dimensional sphere, the projective line. How can one think about this compactification? Let me consider the complex plane and 4 points on this plane, just for points in general position, so that no 3 of them belong to one and the same line. We take points x1, x2, x3, and x4. Now consider quadrics passing through these points. Ellipses, curves of degree 2 passing all possible quadrics. A quadric is a projective line, so that if you have a smooth quadric through passing through these points x1, x2, and 3, x4 is a projective line with 4 marked points. 4 marked points. And in this way we obtain all the smooth genus 0, all the smooth genus 0 curves with 4 marked points, and each such curve we obtain in exactly once. The compactification we have consists in adding to this space of smooth quadrics, we add 3 singular quadrics. A singular quadric is a pair of lines, passing through these 4 points. Since there is, each line passes through 2 of the points, and since there are 3 ways to split 4 points into 2 pairs, we obtain 3 singular quadrics that compactify the moduli space of genus 0 curves with 1 pole. So that to each of these points punctured from the CP1, we associate a singular quadric, or what is the same, a pair of intersecting lines. And these 3 pairs are different only in the way the 4 points are split between the 2 lines. For example, for 0 we have x1 and x2 belong to one line, while x3 and x4 to the other one. For the point 1, we have x1 and x3 on one line, and x2, x4 on the other one. And for the point infinity, x1 and x4 belong to one line, and x2, x3 belong to the other line. Now, a general definition, or maybe a general explanation, asserts that the Deligne-Markov theorem states that each moduli space M, G, N admits a compactification M, G, N bar containing MGN by stable genus G curves with n marked points. With n marked points. Here, what are stable genus G curves with n marked points? First of all, a stable curve is allowed to have singularities. like in this example, a degenerate quadric on the plane is singular. It's no longer smooth. The two lines have a point of intersection, but this singularity is essentially the only one allowed. Singularities. The only singularities allowed are double points, which are points of transversal self-intersection. Transversal self-intersection. Section. First of all. Secondly, after smoothing, points of self-intersection, we obtain a genus G surface. Genus G surface. Singular points of a stable curve do not coincide with marked points. So that marked points remain smooth points. The point of intersection is not marked point. The marked point, the two lines do not intersect at the points at which they are passing. Do not coincide with marked ones. And finally, the automorphism group of the singular curve of the curve is finite. So, if we take a smooth curve, a smooth genus G curve with unmarked points, and its Euler characteristic is negative, then its automorphism group is finite. And the same should remain true for the degenerations of this smooth curve, for the case when the degenerate curve is singular. And Delaney and Mumford have proven that each moduli space of MGN, moduli space MGN, is compactified by the moduli space MGN bar, whose points are in one-to-one correspondence with genus G stable curves with unmarked points. I have shown how it is done for the moduli space M04 and M04 bar. What is the moduli space M04 bar? Compactifying the moduli space M04. Now it's a bit easier. we deal with compact spaces, but we deal with compact spaces. They are orbitals of the same dimension as MGN. Nevertheless, their topology remains complicated, and M04, which is just CP1, is not an instructive example. The sphere has rather simple topology, and Witten's conjecture concerns some topological characteristics of these moduli spaces, of these compactified moduli spaces, which I'm now going to define. Which topological characteristics, some relatively simple topological characteristics, which we are able to compute, and which of course rather very weak invariants of the moduli spaces, but nevertheless they carry a lot of information about these spaces. Similarly to the moduli spaces of smooth curves, moduli spaces of stable curves do not go with alone. And there is another moduli space CGN, which maps to MGN in such a way that there is a map in PGN, so that if you consider a point here, which corresponds to some curve, to some genus G curve C with n-marked points x1, xn, then its pre-image PG n minus 1 of this point is exactly this curve C x1 xn, so that the fiber of this mapping is exactly the curve C, so that the dimension of CGN is dimension MGN bar plus 1, just 3G minus 3 plus minus 2 plus. We have a picture like that. We have some huge space MGN bar, and we have, this is our CGN, whose fibers are the curves mapped to the corresponding points in MGN, and also this space is endowed with structure sections corresponding to the marked points. Each marked point defines a section of this mapping in CG. Now, at the point xi, and the marked point xi, we can consider the tangent line to the fiber at this point. The fiber is the curve C itself, and we can consider the tangent line to this fiber, to the curve C at the point xi, which these tangent fibers ought to be usually people use cotangent lines rather than tangent lines at these points, and they form each this cotangent line forms a line bundle over MGN. So that this is Li over MGN bar is the line bundle of cotangent lines to the fibers of PGN at the ice mark point. I here varies from 1 to n. We have n line bundles over the moduli space MGN. Now, the topological characteristics we are going to consider are related to these line bundles, and they are denoted as the integrals over MGN bar of psi 1 to the power m1, psi n to the power mn, where m1, the sum of these degrees, m1 plus m2 plus so on and mn, is nothing but the dimension of our moduli space, 3g minus 3 plus. Since there is no difference between the points x1, x2, xn, these numbers are symmetric with respect to permutations of the indices 1, 2, n, and so on. They depend only on the collection of these powers. That is why we can denote them tau m1, tau mn with angle brackets. How should we understand this integral? What is this integral about? It's, in fact, it is not directly related to some integration of some differential form over a variety, over a manifold of big dimension. Instead, these are what are called intersection numbers. Intersection numbers or characteristic numbers. Let's compute. I will show how to compute this number in the simplest cases. The easiest such number is when we take t equal to 0 and n equal to 3, sorry. We consider 3 points on the projective line. We know perfectly now that m0 of 3 is the same as m0 of 3 bar. It is just a single point. And we may integrate over this space the product of psi classes psi1 to some power m1, psi2 to some power m2, psi3 to some power m3. But we need that m1 plus m2 plus m3 should be equal to 3 times 0 minus 3 plus 3, which is 0. The dimension of the space, and so that all the power degrees m1 must be equal to m2, must be equal to m3, must be 0. So what we integrate over a point. The function 1, what we obtain is definitely 1. We cannot obtain anything more complicated. In the case of g equal to 0 and n equal to 4, the situation, this is the first interesting situation. M04 is a part of M04 bar, which is just CD1. And we must integrate the class psi1 M0 over the space M0 for bar. It's no matter which class we integrate, psi1, psi2, psi3, or psi4. There are 4 such classes. How does the integration look like? In order to make this integration, we must construct some section of our line bundle L1. So we construct a section sigma from M0 for bar to the total space of the line bundle L1. An element of this section is a cotangent line. It is a cotangent line, so we might here we have M04, and we must take a cotangent vector, an element of the cotangent line at x1 at each point. Then what we obtain will be a section. What is a cotangent vector? It is a value of some differential one form. When we take the differential one form, omega, let me introduce indices, omega 2, 3, which is that has having poles of order 1 at the points x2 and x3 such that its residues at the point at x2 is negative. Its residue at the point x3 and is 1. By picking two poles and the residues of these poles at 2 points, x2 and x3, I define the one form W23 uniquely, and the section sigma, just takes a point to, let it be C, x1, x2, CP1, x1, x2, x3, x4 is taken to the value of this one form omega 2, 3 at the point x1. We constructed a section. Of our line bundle L1. And in order to say what this integral is, that is, what is the integral of psi 1 over m04, we must analyze what are the poles and the zeros of this section C. At the smooth part, and the part where the curve is smooth, this section has neither zeros nor poles, simply because a one form on the projective line that has 2 poles of order 1 and no other poles have no further poles and no further zeros. And it is easy to see that when we extend this section by continuity to the 3 singular curves we have added, what we obtain will be nice if in which situation? If x2 and x3 belong to belong to the either x2 or x3 belongs to the same line as the point x1. In these cases, there will be no zero and no pole at x1. But if x2 and x3 belong to the same line of the 2 intersecting line, then our extended form omega 2, 3, extended one form omega 2, 3 should vanish on the whole component containing the points x1 and x4, simply because it does not have any pole on this component, which means that its value at x1 is 0, which in turn means that the intersection index of the class psi 1 over m04 is exactly 1. And it happens that it is rather easy to compute these intersection indices for genus 0, intersection index. The genus 0 intersection indices are just binomial coefficients. Tau m and r this M1 M are just n minus 3, not binomial, but multinomial coefficients, M1 and M, which are the fractions, the ratios of factorials. N minus 3 factorial, L1, M1 factorial, sorry. Sorry, I have made a mistake. I've made a mistake in notation. Here it is a K, here it is a K, here it is a K. No. This formula is incorrect. This formula is incorrect. How should I? No, it's okay. Another factor. We know that M1 plus M2 plus Mn is equal to Mn. Everything is okay, but I should say that this is 1 is tau 0 cubed. This means that each of the classes psi 1, psi 2, and psi 3 enters into this formula with degree 0. This is let me write that. The integral of psi 1 to the power 0, psi 2 to the power 0, and psi 3 to the power 0. And this is the same as the integral of psi 1, psi 2 to the power 0, psi 3 to the power 0, psi 4 to the power 0, which means that this is nothing but tau 0 cubed, tau 1. Yeah. So we see that for g equal to 0, these numbers are integer numbers. Integral numbers. There are no fractions. That's due to the fact that for genus 0, m, 0, m, as well as m bar 0, m are manifolds rather than just orbitals. They are manifolds because a CP1 with n marked points for n greater than 2 do not have non-trivial automorphisms. That is why these are manifolds. But starting with genus 1, what we obtain are orbifolds. They have non-trivial automorphism groups, and the corresponding intersection indices will be fractional rather than will be fractional rather than just integral. Great. And now it's a true moment to state Wigton's conjecture, which concerns the generating function f that depends on infinitely many variables, T0, T1, and so on. And this is defined as the sum of tau m1, tau mn over n factorial t1, t1, tmn. So this function incorporates our knowledge about all the intersection indices in the moduli of psi classes in the moduli spaces. Its coefficients are exactly these indices divided by the corresponding factorial. And you may look at the beginning of this power series. It starts with plus 1 over 62 cubed plus 1 over 48 t1 squared plus 1 over 6 t0 cubed t1 plus 1 over 24 t0 t2 plus and so on. It is an infinite series, parts of which we have computed. For example, this 1 over 6, t0 cubed is exactly corresponds to our computation of t0 cubed, tau 0 cubed in the brackets, which is 1 over 6 t0 cubed t1 corresponds to this computation. We have one here. A huge series in infinitely many variables, parts of which we know. And the question is how to compute all the coefficients. The question is how to compute all the coefficients of this power series. And the answer is given by Wigton's conjecture. Which states that f satisfies the Carteret-de Vries equation. Partial differential equation. This equation looks like, just to be sure, instead of considering the function f itself, it takes its second derivative with respect to the variable t0. This we denote this function by u, and the Carteret-de Vries equation for u looks like du over dt1 is u times du over dt0 plus 1/12 u cubed u over d0. What is the main feature of this equation? It is nonlinear. It contains on the right the term u times the derivative of u over the variable t0. The two other terms of the equation are linear, and if the equation would be linear, then it would be rather easy to solve. In this situation, we are unable to solve this equation explicitly because of this nonlinearity. However, exactly this nonlinear term can be considered as a recurrence relation for defining a recurrence relation for the coefficients of our power series u and then for the original function f. It is a recurrence relation which allows one to compute all the coefficients of the power series f, starting with this initial condition. We know the intersection indices for genus G curves, for genus 0 curves, with arbitrarily many marked points. And this allows one to compute all the other coefficients. This power series is called now Witten-Kontsevich potential. And the proof that this potential indeed satisfies this partial derivative equation can be achieved in a number of rather different ways. But all these ways should have to include somehow our understanding of the geometry of moduli spaces of curves. And the proof I will explain in the next hour is the one belonging to Maria Mirzakhani, and it uses the hyperbolic geometry of the moduli space. And up to now I have said nothing about this hyperbolic geometry. I was talking only about the algebraic geometric properties of the moduli spaces, but Mirzakhani's proof requires understanding the hyperbolic geometrical properties. Let me stop here and make a break.
Он не будет перебивать с таким трудом открытую трансляцию?
Нет, конечно. This is a non-linear.
съездили.
Хорошо, спасибо. До Ирвана я, правда, не доехал, у них там,
Кто есть?
ну, забастовка у них там.
Как обычно.
Еще в этот раз она какая-то более серьезная, чем обычно.
Это из Швейцарии во Францию, да, поезд?
Ну, по Франции не ходят поезда,
Ага.
в Швейцарии все нормально, во французской поезд ничего не ходит. Поэтому я так до него и не доехал. В самой Швейцарии интересно было. Но там была геометрическая теория, не знаю. То есть это как бы, я немножко сбоку.
У меня друг занимается, Петя Косенко.
Ну, я знаю его, я ему писал рекомендацию для постдока.
Да.
Ну, я немножко занимаюсь, но как бы это не самое. Чуть-чуть. Вот. Но там собрались такие люди значимые. Смотреть было все равно интересно, хотя понятно, там, условно говоря, каждый второй доклад. Ну и место очень красивое.
А это где было?
Диаблера, где-то в горах.
Ну да.
Правда, ну, те, кто прям серьезно катается на лыжах, будут разочарованы, потому что снег хватает.
Сейчас не лежит, да?
Ну, там надо в специальные места забираться. А вообще там такое место, что когда много снега, то можно выйти из отеля и сразу ехать или выходить на гору.
Ну, в Финляндии так.
Дорога.
Мне нравится больше всего, когда мы на склоне Финляндии, поэтому склоны сами там очень пологие, трассы как бы там длинные, но пологие. То есть как будто по парку прикинете вниз туда. Ну, потом там на подъемничке вверх. Вот, но там огромный плюс это в том, что вот этот вот, ну, курорт Вея, да, там прям выходите и просто можно на сноуборде там или на лыжах как сразу до склона.
Вот тут так сейчас не было. То есть нормально, когда зима прям, то так можно делать. А сейчас там вокруг самой деревни уже все растаяло, что куда-то идти. Ну там не цветочки, а грязь такая.
Ну да, ну почти.
Вот, и поэтому нужно было там куда-то ехать и идти. Вот. Но так гулять, ходить все равно интересно. Потом там рядом у них есть ледник на 3000 метров высотой. И туда выходит фуникулер, можно
Просто близко. Ну,
да. Можно покататься там, просто посмотреть. И я просто все равно понравилось.
Okay, great. Now this part I will erase. And up to now, what we were working for are algebraic curves, complex curves with a complex structure. Another object are two-dimensional surfaces, two-dimensional orientable surfaces endowed with hyperbolic matrix. Of constant Gaussian curvature, -1. And there is a one-to-one correspondence between these two-dimensional surfaces and complex curves. In the case of negative order characteristics. So, from now on, we imagine something some two-dimensional surface endowed with a hyperbolic structure, a hyperbolic metric. And now, if we consider in such a curve, in such a surface, some homotopy class of a closed curve, I don't know, let me draw something more complicated, probably. Is it more complicated? It looks like being more complicated. Then, in each homotopy class, of a closed curve on the surface there is a unique geodetic. Of the metric we are considering. So if we take some simple curve, then there is a unique geodesic curve that has the same homotopy class as the one you have chosen, and this is true for arbitrary, I don't know how to draw this, probably it goes like that. There is a unique geodesic. This fact we will use extensively further during the current hour. And in addition to closed two-dimensional surfaces, one also can consider surfaces with boundary, hyperbolic surfaces with boundary. Surfaces with boundary. And I will always assume that the boundary curves are geodesics. Boundary geodesics of our hyperbolic metric. And the length will be denoted L1, L2, up to Ln. There are n boundary geodesics, n boundary curves. Each boundary curve is a geodesic of our hyperbolic metric, and the length of these geodesics is L1, L2. So, what does Mariam Mirzakhani consider? She considers moduli spaces MG of L1, Ln. These are genus G hyperbolic surfaces. The moduli space. Right. space of genus G hyperbolic surfaces with n boundary geodesics. Boundary geodesics. Which are flanks L1 and so on L. Once again, these are smooth hyperbolic surfaces, and in addition to smooth hyperbolic surfaces, we are able to consider singular hyperbolic surfaces, like similarly to the complex curves, our surface can admit degenerations, and these degenerations are exactly of the same form as for complex curves. These are, in this way, we compactify the moduli space of, we compactify the moduli space of genus G hyperbolic surfaces by adding to this space singular surfaces, where the only singularities allowed are transversal self-intersections. Self-intersections.
And the genus is calculated how?
The genus is defined as, if you have some boundary, you simply add a disk instead to this boundary. Attach a disk, you obtain a closed surface, and the genus of the surface is the genus of the resultant surface, and particular here, genus is a now, these spaces are compact. These are also compact orbifolds. And we are interested in the volumes of this space with respect to Weyl-Peterson volumes. Please have a look whether I've written Weyl-Peterson correctly.
I don't remember how.
Yes, you were.
Yeah. So, what are the Weyl-Peterson volumes? In order to introduce the Weyl-Peterson volumes, I need to introduce first the Weyl-Peterson. The Weyl-Peterson simply.
Peterson,
I just checked, it's double S.
Peterson is
That's-
Weyl is correct.
Yes, Weyl is correct.
Double S needs a double check. Well, Peterson volumes, and I have to introduce first the Weyl-Peterson form, and in order to do that, I need to introduce coordinates of these moduli spaces, and these coordinates are Fenkel-Nielsen coordinates. What are they? Let me first consider Fenkel-Nielsen coordinates. Fenkel-Nielsen coordinates with just for closed surfaces, not taking the boundary into account. If you take
just in case you are interested, Nielsen also and
Nielsen, yeah, requires, yes, Lando.
yeah.
Danish people are complicated.
yes, there's too many alphabets.
As I have already mentioned, in each homotopy class of a closed simple curve, there is a unique geodesic. And drawing some closed geodesics of this form, we are able to split, if we cut our surface at a set of 3G minus 3 closed simple geodesics. We are able to cut our surface into simplest hyperbolic boundary surfaces with boundary that are called pads. These are pads. Each geodesics has a length, and let us denote the length of these geodesics. L small 1, L small 2, L small 3. Now, a theorem, an easy statement from hyperbolic geometry, asserts that there are only one band with length L1, L2, L3 of the boundary components. So, if you consider the space of pens and denote with hyperbolic metric of given Gaussian constant curvature -1, then this space is exactly the positive octant in R3. In R3, where the length of the boundary components determine the bands uniquely. By the way, let me mention that the dimension of the space MG bar of L1 Ln is exactly 2 times 3g minus 3 more 7. This is a real orbifold, and its real dimension is 2 times greater than the dimension, than the complex dimension of the corresponding mobilized space. Now, in order to reconstruct, we have cut a surface into a number of pens so that it can be obtained by gluing it back, the pens back. But having a set of pens, the gluing is not unique, because if you choose some curve here, let it be just gamma. Let it be gamma, let, for example, L1 be gamma. And we have the other pair of pens. Of length with L1 prime equal to L1, L2 prime equal to L2, L3 prime equal to L3, which, and here is also gamma. Gamma prime. The gluing of gamma to gamma prime is not unique. We are able to rotate the curves with respect to one another. If we have a point here, if we choose some point on this boundary of the pens, then this point is somewhere here, and we rotate the boundary curve in such a way that the 2 points match one another, so that we have to each cutting curve gamma I, gamma I, gamma j, varies from 1 to n is 3g minus 3, so are associated a pair of Li, a pair of coordinates, Li tau I, so that Li is the length of the cut, and this is the rotation angle of the glue. Of 2 boundary components of the pens, which is well defined modulo 2 pi. And these are exactly the Fenchel-Nielsen coordinates. These are the Fenchel-Nielsen coordinates of the modulus vectors. The same can be done, of course, the same can be done for surfaces with boundary. Here there is no need to, some of the pens will have boundary components as the boundary components of the surface as the boundary components of the pens, and the corresponding coordinates will not include these boundary components. corresponding means and coordinates. And now we can consider the symplectic form dli with d to I, where I varies from 1 to this big N, and this 1 to 3, and equal to 3. In the case we have surface with boundary. And this is exactly the Weil-Peterson symplectic form. It is good because the theorem due to Weil and Peterson, I believe, states that this symplectic form does not depend on the choice of Pann's decomposition of our surface. Fine. It doesn't depend on the Pann's decomposition. Great. And now we are able to define the Weil-Peterson volumes. Weil-Peterson volumes of Mg and 1 Mg of L1. Yeah, let it be the volume G. Volume G of L1 Ln as the integral over mg bar of L1 Ln of the appropriate power of this Weil-Peterson Weil-Peterson symplectic form. The appropriate power is exactly 3g minus 3. Taking this true form to this power, we obtain taking this true form to this power, we obtain a differential form of the highest degree, of the degree which is equal to the dimension of the space, and then we are able to integrate it the resulting volume form over the space itself and obtain the volume of the corresponding space. I must add that none of the steps here is trivial. For example, this Wade-Jefferson symplectic form is well defined on the moduli space MG of the moduli space of smooth curves. It is bound. If we instead consider the moduli space of possibly singular curves and G bar, we must extend somehow this symplectic form to the surfaces, to the subset of surfaces that are singular, and it is a non-trivial extension. There is a theorem by Wolpert where he proves that there exists a smooth extension. It is no longer algebraic, it's only smooth. Nevertheless, it is fine, and we are able to we obtain a symplectic form whose appropriate power can be integrated, but the argument here is not trivial. And now a theorem. Let me write down some volumes just to show how they look like. So that this formulas would not be some abstract. If we take curves of genus 0 with 3 boundary components, then the corresponding volume will be just 1, simply because, as I have mentioned, there is a unique point, there is a unique point with given lengths for each set of lengths. There is exactly one pair of points, so that the moduli space consists of a single point and its volume is 1. If we take M0, if we take 4 mark points, 4 mark points on the genus 0 curves, then what we obtain is 1/2 of the sum of squares of the length plus 2 times p squared. 2 times p squared and one more probably. And one is 1 over 48 plus L1 squared over 48 plus p squared over. Now, we see the theorem used on Marian Mirzakhanian asserts assert that volume G of L1 Ln is a polynomial. Of L1 squared Ln squared. Of course, this polynomial is symmetric. Doesn't matter which variable is in charge of each boundary component. This is a symmetric polynomial. Degree of this polynomial, whatever is the degree, but the coefficients of the highest degree terms are Witten's intersection indices. So, up to certain factorials. There are, I never remember the factorials. Precisely, but no, I'm not going to write them out. They are obvious. So that this one corresponds to the to tau 0 cubed. This 1/2 corresponds to tau 0 cubed tau 1, and this 1 over 24 L1 squared over 24 corresponds to tau 1. So 1/2 of tau 1. So it is always a polynomial, but somehow we have to, and its leading coefficients, the coefficients of the highest terms, are exactly the intersection indices entering Witten's conjecture. How is it achieved? How can one obtain a result like that? In order to do that, one have to associate somehow to the moduli space Mg, construct some relation between the moduli space Mg L1 Ln and the moduli space Mg bar. This is done like follows. We consider this boundary component and then allow the length of this boundary component go to 0. And each element I tends to 0. Or I, so that in the limit, what we obtain in the limit are kind of punctures. Now there is an action of the n-dimensional torus on MGN bar MG and 1 ln. The ith component of the torus, rotates the ith component of the boundary, and if we add a point on the boundary and add the position of this point to the set of coordinates on the union of these moduli spaces. As a result, these limit points, where the length of each component is 0, of each boundary component is 0, are the fixed points. The limit points. Which are surfaces with punctures. And for these limit points, we already obtained a one-to-one correspondence between these limit points and MGN bar. And after this identification, one identifies the leading terms of the corresponding volume polynomials to intersection indices on the moduli space of curves with marked points. That's one point which relates volumes of Wade-Peterson volumes of moduli spaces of hyperbolic surfaces with boundary to the geometry and intersection indices of the moduli spaces of curves, of algebraic curves with marked points. Now, in order to prove Witten's conjecture, we have to establish some recurrence relation for these volume polynomials, which is essentially equivalent to the recurrence relation given by the Korteweg-de Vries equation for intersection, for the Kontsevich-Witten potential, of for intersection indices. And this part is achieved by a different theorem by Mariam Mirzakhani, which is essentially an extension of what is called Markshane identity. identity. McShane's identity is beautiful by itself, so it is useful to look at it and to understand how it can work. McShane's identity relates to hyperbolic structures of the punctured torus. Hyperbolic torus punctured at a single point. Once again, if you consider some homotopy type of a curve on this punctured torus, then we have a unique geodesic in this homotopy type. And we have infinitely many geodesics. Many simple geodesics. Let's consider the sum of all these geodesics of the expression of 1 over 1 plus exponent of the length of the geodesics. All simple geodesics. McShane's identity asserts that this sum will be 1/2, whatever is the hyperbolic structure on the punctured torus. There is a two-dimensional moduli space of hyperbolic structures on the punctured torus of hyperbolic structures of constant Gaussian curvature -1, but whatever hyperbolic structure we take, the result of summation of over all such geodesics is one and the same, and it is 1/2. The main point here is that it is one and the same, whatever are the hyperbolic structures, and the fact that it is 1/2 is an easy hyperbolic geometry property. Now, how does, I'm not quite sure I'm able to, no, I can. One more theorem by Yuzahani states that which provides the recurrence relation. If you take the derivative over L1, L1 of Vg, L1, Ln, then it will admit a rather explicit equation, a rather explicit formula. It will be 1/2 the integral of from 0 to infinity, double integral from 0 to infinity, 1 over 1 plus exponent of x plus y plus L1 over 2 plus 1 plus 1 minus, plus x plus y minus L1 over 2 Vg minus 1 xy and 2 and then here's all dx dy plus there are two more terms. I will not write them down, but I'll explain. I'm afraid it's better to write down. You see, this exponent are exactly the exponents that enter McShane's formula. 1 plus exponent of x plus y plus L1 over 2 plus 1 over 1 plus to the power x plus y minus L1 over 2. And here we have the sum of all G1 of x, y, L1 of all G2 of x, y, Ly2, Li2 dx dy, where G1 plus G2 is G and I1 united with I2 is 2, 3. And there is one more term which I'm not going to write out, but let me explain where this theorem comes from. It is used to prove the previous theorem about the expression for the volumes as polynomials in the variables L squared. So, what we do? Consider our surface. Consider our surface with boundary endowed with a hyperbolic metric. With components L1 and of length L1 and Ln and so on. And we look only at the first boundary component. Take a point at this boundary component and issue a geodesic from this point, which is perpendicular to the boundary. Vertical. geodesic from a point at the boundary. At the first boundary component. And we follow this geodesic and look what happens with it as we proceed. There are several possibilities. One of the possibilities is that this geodesics returns to the same boundary component at one, to the same first boundary component. Then the same is true for geodesics that are close to that one, and we obtain a whole interval of geodesics returning to the same boundary component. There is, among such geodesics, there is one such geodesics. There is one perpendicular to both at both ends, perpendicular to the boundary at both ends. Now, the proof is similar to the proof of the fact that in each homotopy class of a closed curve there is a unique geodesic. Yeah, you just take the shortest one. You just take the shortest one of these geodesics. Now, if we consider now curve that is close to this geodesics, close to this geodesics, and the union of this geodesics and this boundary component. There are two such curves. You can shift from this geodesic to the left or to the right. There are two components. Denote one component by alpha 1, the other one by alpha 2. Each of these two curves defines a homotopy type of a curve on the surface. And in this homotopy type, there is a unique geodesic, once again. There is a unique geodesic. These two geodesics, alpha 1, alpha 2, and A1, together define a band. We can cut this pants from our surface. As a result, what we obtain is a surface of genus one less than the original one, but with two additional boundary components, one of length x, another of length y. X is the length of vector 1, and y is the length. Now we integrate over all such possibilities. We consider all possible values of x and y, and we consider volumes of this moduli space of smaller genus, but with one boundary component, and we can proceed by induction by the G. Another opportunity is the following one. It can happen that the geodesic that issued from our boundary point on the boundary meets first a different boundary component. It's a different boundary component. Once again, there is a whole interval of points where the issuing geodesics needs this exactly boundary component. And we can proceed in the same way. Mainly, we are able to consider a closed curve that goes first along this geodesic, then goes around the corresponding boundary component, and then goes along the geodesics, along this geodesic from the other side. Once again, what we obtain are the bands. Once again, first we take the geodesic in the homotopy type curves represented by this one, and we obtain paths formed by three curves, three boundary curves, two of which are the existing boundary components L1 and Li, to which we arrived through this boundary, through this geodesic. And the third one is the geodesic in the homotopy type of the blue curve. Once again, we cut the corresponding bands from our surface, and obtain a surface of we obtain either a surface of we obtain a surface of smaller gender, And we are able to, and then we integrate over all possible positions of the third boundary component of the corresponding class. I have forgotten to mention that on the first stage, when we have cut off the bands arising from the curve L1, it can happen that there are two possibilities. Either our surface remained a connected surface of genus G minus 1, or it has been split into two surfaces of genera G1 and G2, the sum of which is G. And this is the second opportunity. We also cut off bands, and then we integrate over all possible lengths of the third curve, first of all, and secondly, of the addition of the moduli over the moduli space, the volume of the moduli space of the rest part of our surface. Well, now in fact what we are doing is a recurrence formula for the volumes. This recurrence formula, of course, produces the recurrence formula for the leading coefficients, and establishing that this recurrence formula for the leading coefficients is equivalent to the one given by the KdV equation, Cartevec-de-Vries equation, in the statement of Witten-Skončaty is a non-trivial combinatorial identity, also proved by M. So, I believe, and the main point which is used in this argument is that in addition to the passes I have mentioned, to the geodesics I have mentioned, those who return to the original boundary component, and those which connect to different boundary components, there are geodesics which can go along the surface and have infinite lengths, ending nowhere. They can go around, approach some closed geodesics for infinite time. But fortunately, there is a theorem due to John Bierman, which asserts that the measure of this non-closed, non-bounded, unbounded geodesics is zero. So that this boundary component consists of infinitely many but countable set of intervals corresponding to bounded geodesics, and counter set of zero measure of this unbounded geodesic points corresponding to unbounded geodesics, so that this counter set of points corresponding to unbounded geodesics does not affect the relation of the volumes. The volume of the corresponding subsets is zero. So, the argument by Malyan and Zakharian proving written conjecture is rather complicated. It exploits a lot of extremely non-trivial facts about the geometry of both hyperbolic surfaces and the spaces of hyperbolic surfaces, including the spaces of singular hyperbolic surfaces. But it is definitely, and it also requires combinatorial skills that should be very non-trivial to prove these combinatorial identities I have only mentioned about. But the argument is beautiful.
Could you remind me about the generalized machine identity? Like it's used somewhere in the proof, but I forgot.
Yeah. Essentially, it states that the sum of the lengths, this generalized machine identity asserts that the sum of the lengths of this interval is equal to the length of the circle. We consider intervals. We consider these intervals.
So essentially, she says like if we take all the hyperbolic structures in the modular space and they have the same LIs, then for them this would be like the same number, and then we would just assign them this integer, this fractional number, and then we integrate. That's why we can avoid the modular space thing, like complex underlying. Ну, короче, мы можем не рассматривать комплексные структуры, а только длинный дырок, потому что у нас есть вот это вот generalized.
No, essentially no, because we have essentially not because we have some formulas for the volumes, but we have somehow to establish a relationship between these volumes and the intersection indices of moduli spaces of the classes we consider moduli spaces of caps. And this establishment, this relationship is established by considering the limit points of these moduli spaces, which arise as the lengths of the boundaries tend to zero. Okay, I believe I must stop here. Let me. We are done for today. How should I? Turn off.